about, the big picture, wire to water. We're going to go through the product a little bit, performances and capacities. We'll talk about, this has been a big topic for me, has been low temperature heating. And I've worked with, coming out of the rep world and then prior to that in the field, I think the biggest part of launching a product like this or really growing a market with air to water is really understanding low temperature heating systems. And that has been my go-to since day one of working with air to water systems. The hardest thing to do is to get a contractor comfortable with heating the same homes he's heating currently with lower water temps, 120 degrees, 130 degrees or less. There's such a comfort level, and I just spent a week, different climate from where you guys are, a little bit mid-Atlantic right now, but just the conversations I've had with contractors and probably touched close to a little over 100 people in 3 days. And it's getting them comfortable with getting away from 180 degrees of water, which is something very common. Everybody, and it's trying to grasp that idea that we can do it. And it's not about temperature, it's about BTUs we put into it. Just like our boilers, we want our boilers to condense. They're going to be super efficient when we get low water temps coming back to them. Our heat pump is no different. So the conversations that you may be having going forward with contractors don't have to really be so product driven as they are more system application driven, as far as applications with low water temps and understanding how we can apply this product to heat those homes. So we'll talk about that a lot. Installation basics, all the kind of meat and potatoes there on how we install one of these. We'll go through the control, because that is probably my favorite part of the machine here. And I think seeing a lot of other manufacturers in the past and what they brought to the table, this is hands down one of my favorite controls as far as simplicity, navigation, even troubleshooting. So it's been a lot of fun working with it. We'll talk a little bit about strategy and targets, some of the people that I've seen, the people that I've had conversations with, the people that you may want to go look at. And obviously Q&A happens throughout this whole process. So if you have it, throw it out there. So when we talk about air to water, and I know even up north where you guys are, mini splits have been a popular item for many, many years. And what I found here, and I did some research on rebate driven heat pump systems like mini splits and ductless systems. And what it was interesting, this is one little tiny, I guess you could say, just a look at rebate installations over a couple year period. And this is one utility kind of north from us, at least for me, it's northern, and it's Vermont Energy was the utility here. And this was all systems that were installed through a rebate in their area. And mini splits, you can see obviously that growth from 15 to 2020, but from 2020 really to today, it's really just kind of flatlined, if you would. It's, less than 10,000 units right there on that line. Unitary or ducted systems kind of came back, as you can see in the orange there. But it kind of plateaued, and there's a lot of challenges, and we're going to talk about them right now when it comes to refrigerant-based systems and refrigerant-based heat pumps. But when you look at the air to water side of the world, that's where they started plateauing, we started kind of growing in air to water. And this is not a huge market, but it's going to get there, with all the challenges we can see. From 2020, obviously, to 2024, a heck of a lot more installations on the air to water than there were in the past. Before 2019, they were actually non-existent because the utility obviously didn't have a program in that part. So air to water, obviously that market is a little small right now. It's growing. The conversations we're having, the homeowners that are being educated right now, it's been a lot of fun over the last 8 years, working with this product. So when I said challenges before, when you think about refrigerant, especially in the States here where I am, refrigerant and A2L changes that we're seeing across the board with manufacturers have been not the easiest to deal with. And when it comes down to putting refrigerant now into a space and all the work that's needed, as far as calculating room volume and understanding if you need ventilation or leak detection or whatever, the contractors are kind of in the dark. And, it's not a good look for a lot of them. A lot of them are installing stuff. They don't even know if they're following the guidelines, which is kind of scary. The education, and that's kind of what I did before I came on board in May, was worked with a mini split manufacturer, one of the fairly large manufacturer out there, Fujitsu, And I spent a lot of time working with contractors, and it still blows my mind talking to these guys and asking them, what are they doing to prepare for, the A2Ls? And they don't know. They have no idea. They don't even know that they have to do these calculations. So there's going to be there's a little bit of a learning curve. The education side is just not there. So I found this, I thought it was pretty interesting, was New York City, where I'm located. Department of Buildings is very similar across many different areas. The requirements, when we look at different electrification options, and working with A2L refrigerants, anywhere where there's VRF, mini splits, multi splits, anywhere you go, they want some sort of a ventilation, right? And in this case, they're showing ventilation shafts to apply. But this is the first time I've ever seen with working, and I've worked pretty heavily in this area. I've never seen them actually call out air to water. So they're really acknowledging that this is most likely the most viable option when it comes to heating and cooling. And they're saying hydronic with central air to water heat pump, and the two asterisks just mean here, avoids all issues with A2L refrigerants. So, in my eyes, I'm seeing this, and it's not just New York City, it's all over the country in major cities, is they're trying to avoid having this refrigerant in the space, and water is just, in my eyes, the best media for it. I ask guys all the time, and this is something you can ask your contractors because it really opens up the conversation for air to water, is I ask, I try to go around a room and see who's been doing it the longest. And I love to ask them how many refrigerant changes they've been through. And the reason I ask that is it starts all kinds of grumblings. And they really, oh, I've been through 3 changes, I've been through 4. They understand that there's challenges with change. And when I ask them now, what about water? When's the last time water changed? And they're like, well, never. Right. So if it never changed, wouldn't it be easier to work with, especially down the road, if there was any look at replacing of a system, the outdoor unit is the only thing we have to look at. It's a quick swap. Everything inside stays the same. And that's where their ears start to perk up and listen a little bit. And this is just something I found talking about water being used in heated water pipes beneath floors, going back all the way back to the ancient Rome. So, we know it's a great media. It works great with radiant heating and all low temperature applications. It's just really applying this product properly. And that's been mainly the conversation with contractors going forward. This is a great slide. We're just talking about the benefits of using water, and just kind of a comparison of air and versus water. Is with water, I mean, we can be pretty creative when it comes down to zoning. When you look at air systems, ducted systems, it's very difficult to get zoning correct. Most cases, you'll see 2 zones, and even that half the time isn't working properly. It works, but it's not working properly, and it's not efficient, and it's really killing the machine prematurely. Finding somebody that really does zoning properly is pretty rare these days, and has been for a long time. The zoning with water is pretty simple. These guys can get as creative as they want to be. We see these projects all over social media where they got 10, 20, 30 zones of hydronic heating. It really just comes down to that ability to size a circulator or a pump, right? Or I should say a pipe. This footprint, this has been something there is with buildings, going forward, they're giving us less and less room to put our products, right? And when you look at the comparisons of pipes versus ducts, just as an equivalent, you can carry about 40,000 BTUs through a 3/4 inch pipe. To do the same on the air side, you need about equivalent to a 10-inch duct, round duct. So the footprint itself is so much smaller. Most architects, engineers, and builders, they want to, maximize their square footage, and we can help them do that with the smaller pipes that we run. Integration, we're going to talk about that a lot today, throughout this presentation. When we go through the control side, we'll talk about that more specifically, but integration with existing hydronics and heating systems is probably the best option for us. We love hybrid systems. We love our boilers. We're not trying to put ourselves out of business here. We know that there are certain parts of the years that may be more efficient to run an electric versus a natural gas or propane. The nice thing is we get to select when that is. The contractor has full flexibility. He can choose what temperature he wants to basically utilize the boiler or whatever the backup heating system may be. It doesn't have to always be gas, or it could be oil, it could be electric, it could be really anything we want. So hybrid systems is a big focus of ours. Better dehumidification, 100% with water over refrigerant. Water itself, non-toxic glycol, That's the most we're going to have to deal with when it comes to water quality on an air to water system. And that really is the maintenance. The maintenance is making sure we have the right amount of glycol, make sure it's not corrosive, making sure we have maybe some inhibitors if there's metallic parts in our system. So that's more of the focus on maintenance. Whereas with a refrigerant-based system or an air-driven, like a heat pump or something like that, you're dealing with a lot of, refrigerant guidelines. You have to, if you had a leak in a system, you had to make repairs in a system. There's recovery, there's, actually fixing it, then pressure testing, evacuating the system. It's a lot of time and money to sit there on a job and do it. And most people are not doing it right because they know how expensive it is to do. And indoor air quality. So anytime you think about moving air versus moving water, right? We're not spreading germs, viruses, bacteria, all this stuff that may be airborne with a hydronic system. We're moving water through a pipe, right? Where when you think about a centrally ducted system, we could be moving that air from room to room, especially with a central return. You're basically injecting everything in that space into the other rooms. So it's a lot easier to get sick. So better indoor air quality typically with water-based systems. So how does it work? So I don't know the skill level of everybody on the call today. So I'm kind of going to give you not give you a headache here, but kind of give you an understanding on how it works. So if you do know, maybe it's a little refresher. If you don't know, if it's too complicated, feel free to stop me, throw it in the chat here, ask, throw a question out there, and I will stop and explain this as many times as we need to. But basically, we have two different types of systems that are out there in the world today. We have monoblock heat pumps, we have split system heat pumps. So meaning that all the refrigerant components are going to be inside that outdoor box. So there's nothing to the occupancy. So we're moving, as you can see in the top there, we're moving basically, warm water in and then returning it back to the machine. Whereas a split system, we have two components. We have an indoor box, which usually will house a refrigerant to water heat exchanger. So we're moving refrigerant from the outdoor unit into that indoor box, and then we transfer that energy into the water indoors. I think, this is kind of I think one of the most confusing parts of these systems, or not confusing, but it's almost like we've heard many times that we don't need glycol if we went in with a split system. And that's kind of a false statement there, where you don't need as much glycol in the system when you have a split system here. You do have very cold refrigerant, especially if we're moving chilled water, that's going to go through that refrigerant to water heat exchanger. So if you got really cold refrigerant on one side and water on the other, well, if you put no glycol, there would be some opportunity possibly where if that refrigerant got too cold, you could freeze the water in a flat plate heat exchanger, and that could do some damage as well. So those are your two different types. If you're not sure how it works, right, I got a couple components here that we'll call out. We have an outdoor fan, we got a compressor, we have two exchangers inside the unit. We have an air to refrigerant and we have a refrigerant to water. We have an expansion valve down at the bottom labeled as an EEV. That's an electronic expansion valve. Water in, water out, all of that. So if we turn that fan on and we start moving air through that large air to refrigerant heat exchanger, we start moving that air across there. When that compressor kicks on and starts moving refrigerant through our system, as it comes through the system and goes through our metering device here, or our expansion valve, we get a large pressure drop through this coil. So the lower that pressure drop, if we drop pressure, we also drop temperature. So we're going to talk about, you're going to look at the refrigerant we're using, which will be R32, and we look at the boiling point of that refrigerant, which is down at about -61 degrees. When you hear boiling, most people think of hot, right? It's got something that's going to burn you. In this case, the lower that boiling point of a refrigerant, the colder it is. So if I were to take the air that's going through this coil, let me see if I can get a little laser pointer here. There we go. If I were to remove and shut this fan down, removed all the airflow through this coil, if I had a low pressure, really cold boiling point here coming through here, that coil would freeze almost instantly. So we need the airflow going through there to warm up that coil. And basically what we're doing is we're now taking the heat out of the air, absorbing that in through the coil into the refrigerant, and then we can then boost that temperature up and get hotter temperatures here, which will now absorb itself into the water going into the home. So when we hear boiling point, I got a couple different slides here. Let me see, maybe next slide will be a better representation of that. But you'll hear things like -13, right? Heat pumps are rated at different temperatures. I typically don't look at those. Those are the low performance numbers. That's kind of where we rate ourselves at. But -13, and if you see somebody else with a -15 or a -20, we're all kind of restricted on performance based on the refrigerant we're using. We have controls that may get us to different temperatures, but we're really just, everything's restricted based on a refrigerant. So as long as everybody's using R32, which is the case with most, and if not all, heat pump manufacturers right now, as far as air to water systems go, you have that limitation there. So when you're pulling that air through, what we're looking for is a temperature difference, a large temperature difference. The larger it is, the more energy we can transfer at a quicker rate. So when we think about the fans that we have, this is just a fun little thing I put in here because I wanted to know, personally, what is the coldest temperature that we can still, or there is still energy in the air. We can't really use it. It's not usable energy. Plus, we wouldn't survive in an absolute zero environment. But at -459 degrees Fahrenheit, or in your world, 273 degrees Celsius, that is super cold, but there is still enough energy to pull out of the air. Not enough to heat a home, but there is energy in that air at that point. We're talking about -13 as a low temp, right? So we still have, if anybody asked, well, how efficient is it or at that temperature, we have some charts we can look at that'll tell us that. But for the most part, single digits, down to zero, we're still really damn efficient with these machines. So we'll take a look at that. But this is kind of that difference in boiling point and ambient air. When you think about each one of these fans in a unit, now this is a 5-ton unit having 2 fans. We have about 3-ton, which is a single fan. You'll see that in a minute. But each one of those fans brings about 2,000 CFMs of air through that coil. So if I'm moving that much air and I'm coming across, if I had a 32-degree Fahrenheit, 0 degrees Celsius day, right, and I had a boiling point, and that refrigerant was at -50, right, that's a huge temperature difference. So we're absorbing a lot of energy right through the air into that coil, which we then boost up, like I said before. We send that into the water and we're putting it into the home. So boiling point is just something that, if you're not used to refrigerants, it can confuse you. But if, like I said, if there's anybody that didn't understand, please throw it in the chat and I'll go back to it. When we talk about COP, right, that COP is our efficiency. So if you're familiar with our boilers, we talk about AFUE, that's how efficient that boiler is going to be at a given temperature, right, different CO2. So we have some different criterias there on the combustion side, but AFUE is really affected too by the water temps that we bring back. So the lower we can bring it back, the higher the efficiencies. So if we're bringing, like I mentioned, contractors are so used to pumping 180 degrees through their systems, they're bringing back hot water at 160, 170 degrees. We're really not, running that system properly enough to get that 96% that we're going to say we can get out of that boiler. Typically, it's going to be about, running efficiency is probably going to be somewhere around 84, 85%. So it's very low. Well, with a heat pump, we look at COP as our efficiency metric. So, and that's a ratio between the input over what we're actually putting into the space, right? So if I were to tell you right now, our system had a COP of 4, what that really means is that for every 1 kW of input power, we're going to provide 4 kWs of output power into that space. So if we looked at it BTU wise, 1 kW is equal to about 3,412 BTUs. We put that into the machine, we absorb a lot of energy from the air. We now boost that up, and we're really just transferring that energy from the air, boosting it a little bit and putting it into the space. And now I'm delivering 13,600 BTUs. Right, so it's BTU delivery, and that's one of the messages I've been trying to drive for a couple of years now is don't focus on the water temp. Obviously, we need to design around a water temp, but it's more about make sure we deliver the BTUs that we need to offset and make sure that that thermostat is satisfied. COP, if you think of it as a percentage, right, would be, and it's basically, it stands for coefficient of performance. A COP of 4 is equal to 400% efficient in an electrical world. Right, and I like the dollar approach. It's another easier way to explain to somebody is if you give me $1 worth of energy or input power, and I gave you $4 of energy back, it's a pretty good deal, right? $4 for every dollar you give me, you'd be pretty happy with that, I would say. Now, COP is kind of, it's funny because it's derived at a certain condition. So when we look at our charts here, and this is just a small sample of just for an example, but if I set at 17 degrees outdoor ambient temperature, you know, and I designed around a 95-degree water temp, right? We're looking at a COP of just about 300 at 17 degrees. So COP is given at a certain temperature, right, or a certain performance level. So we're going to look at another one. This is called IPLV, or integrated part load value. And this is a lot more accurate as far as comparing system to system, right? Or manufacturer to manufacturers. We want to look at our IPLV. And basically what that means is we're looking at the entire season, and we're looking at the different load points. So we're looking at, all right, we're not running at 100% all the time. We actually run at 100% about 1% of the time. For 45%, less than half the time that we run this heat pump, we're going to be at 50% load. So we want to see what the efficiency points are at that 25% load, at that 50% load, 75 and 100. And we take a weighted average of those points, and you're going to see a range of IPLV, which is going to give you a better, it's a lot better of a metric to compare other systems by. It's an apples to apples approach, because you don't know what water temp somebody may be using, right? We are certified. We are on the HRI certification list. You'll see there's 6 different certification numbers there. So when designing a system, that will be pretty important to you, utilizing the HRI certificate for these qualified systems. In the States, we have qualified product lists. Up north, you guys may or may not. I have not seen that myself personally, being down in New York my entire life. But if there are qualified product lists up there, what we ask is if you're doing some digging and you're finding out about some kind of programs, let us know. So if we have to get involved and get on there, myself, or we'll start the email chain. Dan's been doing this in the background for a while now, as far as reaching out, finding out what utilities kind of need these or have these qualified product lists, and how do we get on there, and we'll make it happen. You know, that's really what it comes down to. So looking at the product itself. So we have 2 units that are coming out. We have the 5-ton, as I mentioned, the dual fan, and the single 3-ton. For every outdoor unit you're going to install or sell, you're going to have 1 indoor control box or hydro box. Now, this is going to come down to the application. This is going to come down to the contractor. So, you know, they have an option which one they want to use. And I'd love to hear, maybe we'll throw a little poll up. I believe I may. No, I did not have one here. So maybe we'll just do it through the chat. But I'd love to hear which one after this, you know, you would think, you know, would be more of a focus on, or what you would think you would see more of. But right now, it's either the control box or the hydro box, and we'll look at the differences in 2 seconds here. Performance range on the cooling capacity, anywhere from 9,500 to 48,000 plus on the 3-ton, up to 74,000 on the 5-ton. Heating capacity up to 42.9, about 43,000 BTUs on the 3-ton, and 73.5 on the 5-ton. You can see the frequency range here. So this being an inverter piece of equipment, it can ramp up and ramp down from 30 to 90 hertz on the 3-ton and 30 to 76 on the 5-ton. So we can reduce our capacity because of inverter heat pumps now. We also, if you're familiar with heat pump design, it's given us the ability to kind of size smaller on the indirect tank, which has been on the buffer tank, which has given us the ability to kind of capitalize on some space in a mechanical room possibly. So, and we could talk more about buffer tanks shortly. So just a couple features here. Obviously, I mentioned -13 and being a monoblock. We are using that R32 refrigerant. We are DHW capable. We'll talk about that. Max water temps 140. Quiet operation because of that inverter compressor, and HRI certified. As far as the indoor, that's right. I forgot I threw this in here too. I threw this in here just to, you know, because I know some people ask all the time what refrigerant using. R32 would be our case. But this one here, just so you can see the factory charge here. I don't know how much, you know, we actually had a couple guys in class the last week or so say this is pretty popular where they are. Again, this is Mid-Atlantic. I would think this would be more popular up north in Canada, as well as the northern states here, where we do see some applications where they want to put the outdoor unit in an indoor space, you know, whether it be a garage, you know, a parking garage, or, you know, they have some kind of mechanical space that they want to put it in. So one of the things I know with A2Ls has been a challenge is understanding the volume of the space. I know the way some of the codes have been, or standards have been written, is anything less than 4 pounds of refrigerant. Typically, you do not need ventilation, leak detection, stuff like that. So I do make a point that we are under 4 pounds on a 3-ton system and just under 6 pounds on the 5-ton. So potentially, if you had an application in a garage or a confined space, or as long as you had the air volume, I shouldn't say confined space, as long as we had the air volume there, but it was an enclosed space, as long as you're under that 4, and that's what they're looking for, we don't need ventilation and leak detection. So I like to bring that up. Some features on the indoor unit: 7-inch touchscreen, as you'll see, simple setup and diagnostics, simplified wiring, so we give you that nice single location to kind of bring all your inputs, outputs, adjustable heating cooling curves we'll talk about, automatic heating cooling switchover on the control box and hydro box, and then specific to the hydro boxes, we have a PWM circulator inside, a 3 kW auxiliary heater, so for supplemental heat. This is kind of standalone, meaning that we power this separately from what we power the control, and we'll talk about that once we get into some of the wiring. And there is a factory 3-way diverter valve installed as well, and we'll see the inside of that in a few seconds, and you see how well insulated everything is. Control box, exactly what it sounds like. This is going to be, you got the touch screen there, you got a touch screen display board on the back of it. There is a switching power supplied here on the bottom left, control PCB, and then up here is where we would have all of our inputs and outputs. There are some pigtails that are off here. Those are all around sensor locations, so those are all nicely labeled, and you'll see that all the ends of the sensors themselves and even some of the extension cables, they all have a specific label for the sensor, making it a lot easier come install to make sure we're plugging in the right stuff. Mistakes do happen, we get that, but it's easy to kind of identify once you go through it. And we'll go through the labels on the power, the inputs and outputs in shortly. The hydro box, just a little bit differently. Dimensionally, it's a lot different, size-wise, weight, and all of that. We have the same input outputs at the top here, same control PCB, same power supply. We do have an additional set of relays here and a thermostat for the auxiliary heating for that 3 kW element there. So that is standalone wires, or everything we need to connect to it if needed. And then that is, and I'll point this out here, as you can see on the right, there is 2 hinges here. So this door is just going to open up and give you access to the 3 kW element. We have an air vent up here with a nice clear vinyl hose that runs through the bottom of the box. So God forbid there was anything happened to this air vent, there was any discharge of water, it's not going to happen inside the box. We do the same with the relief valve, where that's also got a discharge tube here that could be converted over. There's a fitting at the bottom. You could convert that over with some adapters to maybe copper or something and bring that down to the floor. We have a 3-way diverter, and here's our PWM circulator on the right-hand side there. So just looking at the screen, and we're going to go over this a little bit more as far as getting into the programming and the setup of this machine, but just to look at the display itself, very easy to interact with. I like to compare this to the cell phone you have. It's so simple to kind of navigate, very fast reacting. But what you're seeing on the screen here is we got our mode on off and our settings button here. If the system is programmed properly and we activate the system, you will see a blue light here instead of a red. If that is red, that just means that there's power there, but the system will not run. So we can disable the system from here. The components are still going to have power to them, but we can just shut down everything right from the touchscreen. We can select our modes, so depending on how we program the machine, we'll be able to turn on manually to heating, cooling, domestic hot water, however we have it programmed, or we can do automatic, which we'll talk about in a few minutes as well. In the rooms themselves, we are able to control some heat circuits here. We were able to see what you're seeing in the bottom box there is we have basically a buffer tank set point, as well as the actual temperature that's coming through the system. We can, and I was going to bring it up in the buffer tanks, but it doesn't hurt here either. If we have a system that's sized properly and we have a large mass, let's call it radiant system that is capable of, we're capable of achieving the volumes we need, so we're not short cycling the machine. We don't necessarily need in every application a buffer tank, although it is recommended. You can run without, and this you would take the buffer tank sensor and put it to the return piping going back to the heat pump, and that's how it would control its temperatures. So in this fact, you would see what our set point is, and then the actual temperature of the water going back to the machine. So depending on the application, we have that ability. We're also going to see at the top of the screen here, we got a status of the unit, which will give us, as it shows here, we have proper communication in this system. There may be pumps that are activated. You'll see which ones from here, as well as any faults or even mode that the system is in, you'll see up on top. Then we have our DHW. So if we are utilizing this system with an indirect water heater, you'll be able to set your tank temperature from here and see the actual as well. Ambient is going to give us obviously the outdoor ambient temperature. It is also a quick little advanced views button. So if we click on that, you're going to see something that looks like this. I love this. Contractors so far, the feedback has been great. We had a couple classes already. They love that they can physically see now the hydronic system, as well as you'll see in a second the refrigeration cycle as well. So in this case, you're seeing what they're showing is a hydro box. This is on here regardless of having a control box or a hydro box, but you're seeing a basic illustration of a hydronic system. If you do not have a certain sensor hooked up or a circuit that you're utilizing that's on this diagram, you'll notice that the temperature resorts back to 32 degrees. In my case, this is set for Fahrenheit. So if we were to do, if this was converted to Celsius, you'd be at 0 degrees on your sensors if they were not plugged in. So room temp would be showing 0 degrees Celsius. Mix valves, so we have the ability to control mixing if we were using radiant temperatures or radiant applications, and we had 2 electronic mixing valves, we'd be able to utilize them. More specifically, if you had different temperatures on a radiant. Indirect, you can see our tank temp as far as our setting, and then the actual temperature, which in this case is showing you 32 degrees, which would tell me that it's not seeing it. So we're not using an indirect. We can get into some settings here. It helps if I click and then you can see those identifications. But you have a setting here where we can get more specific with the machine itself. You can see some average temperatures, so just some kind of data down there. We hit the house button, it'll bring us back home. But if we swipe the screen here, just like you would on your cell phone, you're going to see it's going to open up now our refrigeration cycle. So now we can get more data, right? We can see our compressor status. It's going to tell us our frequency, amperage, and voltage. We can see the entering and leaving water temperatures. So now we can kind of get an idea if we have a circulator that's properly sized, if we're getting good heat transfer through it. So we can tell a lot from these numbers, delta T. We're going to see our refrigerant pressures. So if there is somebody, and then again, we're going to talk about targets later, but a big target of mine has been plumbers. Plumbers that are not involved in refrigeration right now, that are not air conditioning guys. These are guys that are perfect for this because they don't necessarily need a license if that's the case where you are. Where we are, we don't need a license if we're not touching refrigerant. So that's a huge step forward for them. They also don't technically need gauges, maybe to confirm, we may look down the road, but if I just need a quick view, I'm getting my pressures here, I'm getting my thermistor temperatures on here as well. And then there we go, refrigerant circuit thermistors. We're seeing our system mode up here, so it's telling us what we're doing. Right now we're in a standby mode. Fault information, if I had anything, this info would turn red. I click on that and it would tell me what's going on with the machine. So a lot of great data just from 3 screens, a home screen, our parameters overview for a hydronic side, for our refrigerant side. So right from here, if somebody was in front of this machine trying to do some troubleshooting or just trying to get an understanding on what's happening at that time, you can look at 3 separate screens. If it's troubleshooting, they can take pictures, send it to us, myself, tech support, anybody involved, and we can help them, get directed into the right area. All right, no questions at this time. All right, so getting into some of the performance, we hit this slide already. Looking at the heating performance, I'm just going to go through this one chart in a little bit of detail, and then the following ones we're going to go through a little bit quicker because they're all the same, just representing different modes and different units. So when you look at our performance charts right off the bat for heating, you can see this is going to be our 3-ton system. There's 3 solid lines and 3 dashed lines underneath it. So the solid lines, each shade of them, it represents a different temperature. So in this case, we use 95 leaving water temp Fahrenheit, 113, and 131. I'm looking at the max the system can produce at that temperature or ambient temperature, and I'm looking at the minimum the system can produce at those ambient temperatures. So being inverter, it can ramp up in that entire range. So if I'm looking at a 5-degree outdoor day, I can come up here and I can see what temperatures I can maintain. And I have another chart you're going to see that's in our manuals. If we're designing around a specific water temp, you can see the extended range and if we're able to get those consistent water temps, which is really nice. So max performance, lower performance on the dashed. And then at the bottom here, I threw the COP charts, right? So here, if we're designing around a certain COP, we can pick that COP if we know what the most efficient, fuel is at that point, and we can look at the outdoor temperatures and see the performance that we would get out of the machine. So this is going to be very common when designing around hybrid type systems. If we have a fossil fuel machine and we have the heat pump now and they're both integrated together, now we can kind of pick and choose at what water temps and at what outdoor temps we want to switch over this machine to maybe an auxiliary heater and switch between, basically inputs, which is really cool. So cooling looks no different. We just chose the minimum water temp of 45, the maximum 64, same concept, max and min performance. And then the 5-ton, same deal, minimum max. When we're designing a system around water temps, this is a cool chart that I've never seen in any other manufacturer's IO manuals. So I was really pleased to see this, because if I was designing a system and I was using a specific type of heat emitter where I knew I had to design in order to get a certain amount of BTUs out of it, I needed to have X water temp. I can come in here now and I can kind of get an idea that, basically from, 100 and looks like about 123 degrees, we'll call it 121 degrees. Actually, it's 122. It's right there. I don't have to guess. From 122 degrees to 95, I'm going to get a consistent water temp throughout the entire operation range here from -13 all the way up, right? So if I were designing a system and my emitter I needed 130 degrees, well, I can tell here that once I get to about 8 degrees Fahrenheit, right, 8 degrees Fahrenheit, I know that I'm going to start to tail off. I'm not going to be able to provide 130 degrees of water below that. So my BTUs may diminish, on my output side, going to those heat emitters. So I got to be careful when I'm designing a system that if I do need that water temp, I can see from this chart, right, I may need to do either bump up the equipment or multiple different things, right? But I have an idea on what consistent water temperatures this machine will be able to give you. Same thing on the cooling side, right? So we can give you, if I needed 45-degree water, right? 45-degree water is going to get me to about 97 degrees outside, right? Typically we see about, 48, 50 degrees, somewhere around there. Some applications maybe a little bit higher, right? Depending on the moisture removal and everything else and the design of that air handler that we may be doing, if we're talking cooled water, which is a very cool application. If you've not done one yourself, we just got to make sure we have good dehumidification somewhere in the system. We don't want to run chilled water through a radiant tube or something like that and not have dehumidification. So that's a whole nother animal. So when we talk about sizing, right, these systems, right, and I spend a lot of time with contractors because this is very important. When we talk about high efficiency, we want to make sure we're sizing things properly. I love to ask them, what program they're using here. So if it's something you guys do in-house or I don't know how that works with you, but the conversation of just making sure these guys are really designing their systems with a manual J and having some kind of load calculation. I try not to have a conversation about, application until I've seen a physical manual J. I don't want to go just throwing equipment out there and hoping it's going to work. We want to make sure they're doing it properly. There's so many different programs out there today for them to use. So it's just making sure we drive that conversation. What we've done and what NTI has done, exactly, there you go, Stacy. So we got that right now. So we have this Verta configuration tool that we have built, and Dan has been a big part of this. So it is a app as well as a web-based platform. So if you want it on your phone, it's great to show contractors. Android or Apple, whichever one you're working with there, you'll have the download. But what you're going to see is if you go to ntiboilers.com and you go to the Verta product page there, like Stacy mentioned, you go there, and what's going to happen you'll see, I think it's the second tab down, it's going to say what size heat pump do I need. So if a contractor knows the load of the space or the building or whatever he's working with, he's going to be able to now kind of get an idea on what or how many heat pumps he's going to need. He's also going to be able to manipulate the program a little bit here, where he can, and I've used this with a couple of one of our reps. Actually, we sat and had a little bit of a fun time with this, playing around with some temperatures. But if they understand their utility rates and they know what they're paying for electric in their home, you know, they can kind of manipulate their designs a little bit, right? Because typically when we look at a manual J, and you know, when you look at a manual J, we're heating our home or picking the equipment for the worst case day, which is a very small percentage. So for here, we can kind of play around with that number. And this is how it works: is you pick your province or state. And for my case, I picked New York because that's where I'm at. It gives me the option of Southern or New York. So I can put in Southern New York. It'll get me more accurate to my weather stations. And you can see two things were pre-populated: my heating design temperature and my cooling design temperature. So this is all based off of ASHRAE data. In this case, my cooling design is 14. Now, if I have, which in case there's an FTBN boiler in this house, if I was going to put, you know, a heat pump in and I wanted it to do 70% of my winter, right, I can go base my design off of, let's call it 40 degrees or even 35 degrees. Well, I can come in here and see what my performance is, you know, at 35, right? And because I don't need it to work, I'm going to do my switch over and have my boiler kick in. I can manipulate these numbers here. They don't have to be whatever ASHRAE says it is. If they understand how to kind of manipulate it, and we'd be happy to have a conversation with them if they were asking design questions, yourselves as well. Also with this, if I was not doing cooling and I just wanted to clean up the app a little bit, I can come down here and I can toggle the heating or cooling, or I can also change my units. So if you wanted the Celsius, I can go there and toggle that. Once I do that, once I have that information, the contractor has to enter the rest of this here. So they're going to take their design load, right, which I put some numbers in here. I put a design load of 31,000 BTUs, cooling load of 22,000. The water temperature, outlet temperature is going to be based off of the application. It's going to be based off of, you know, the temperatures that they're trying to design the system off of, the actual ambient temperatures, as well as the emitters that they're using. If it's radiant, hydrocoils, baseboard, fin tubes type stuff, paddle rads, Tokyo, there's so many of them, which we'll take a peek at. But that's where I'm going to look at, you know, how many BTUs do I need to match at what water temp, and the lower I can do, the better I'm going to be for the machine. The final two things we're going to enter here are the glycol percentage. So when they change the glycol percentage, it's going to, on the output form, which is on the next page, it's going to show them what the duration is based on the glycol percentage. And it's also going to ask for a maximum number of heat pumps. So this is here as a great, you know, if there are any restrictions on the project, they could be aesthetic restrictions where the homeowner just doesn't want to see a bunch of heat pumps. It could be electrical panel restrictions where it just can't handle all the amperage. So we got to keep, you know, maybe minimize it to 1 or 2. They'll be able to kind of manipulate that. If they just leave it alone, it's on infinity. It'll pick it 100% based on the load, and then we can maybe tweak some numbers afterwards. So if I were to come down here and click that confirm button, I'm going to see something like this. It's going to tell me my system heating output of the machine based on my design temp. It's going to give me my system fluid requirement. So this is going to be the minimum fluid requirement of the entire system, all right, or the system with the smallest zone calling, right? I have to have at least that volume there to keep that heat pump from short cycling. I need that volume there for defrost so I can have a proper defrost cycle. So we want to make sure we have that volume. And this is where I said, you know, a buffer tank is recommended in the system. It's there as almost like a safety factor. But, you know, technically, if I had a high mass radiant system with 15 gallons of water in it, and that's the smallest zone that would ever call, it would have 15 gallons, then this system would not need a buffer tank, right? So, you know, when it gets into that, if you have questions, please reach out and we'll be happy to help you with those designs. If I hit the little down arrow here, right, it gave me a recommended system list of a 5-ton heat pump, our NHP 060. So that's going to tell me the heating output of the machine rounded up, just as these numbers are here. It's going to tell me my input as well as my heating efficiency, right, COP at heating design temp. In my case, it was a 14-degree day. So at 196 degrees, 196, I'm sorry, at 14 degrees outside Fahrenheit, and the water temperatures that I picked, I'm going to have a COP of about 196 or 1.96, 196% efficient. It's also going to give me the maximum heating output of that machine, and it's going to give me my cooling efficiency as well. So if I needed that. And we're working right now with the developer of the app, so we can kind of have an output print page where you're able to select whether it's a PDF or an Excel file that you would like that's going to have all of this data between your inputs and your outputs. This way it can be emailed to whoever needs it, and you can build your system from there. So that's something in the works as we kind of work through this now. So this has been a big part. This has been, like I said in the beginning, this has been the conversation I've been having with guys, because I think this is the biggest challenge in the industry, is getting them comfortable. You know, I found this chart here, and the only thing I would change on it is maybe on this traditional cast iron radiators tab is maybe dropping this all the way down to 110 as well. But those are the temperature ranges that these heat emitters are capable of performing at. Right. So when I talk to contractors, I like to throw this out here because that's where they're comfortable. They're comfortable at the maximum temps of all of these systems. But when you see the floor radiant down here maxing out at 140, this is where I like to ask them, you know, if they've ever installed a radiant system, or if they haven't installed one, have ever worked on one. And a large majority, if not every contractor I've come across, has always said yes. And then I ask them, well, what temperature was it running? And you hear 95, 100, 110 degrees, right? Something around there. And that's, again, are your customers comfortable? Is that radiant system working? Does it heat their home? Are they happy with it? You know, and yes, of course they are. Well, great. If it's worked at 100, 110 degrees with the radiant, then why can't it work with all of these other systems? And again, that's where their ears start to kind of perk up a little bit. My goal is to get them comfortable with this. You know, that's been the conversation, is getting them more comfortable with that type of stuff. Now, I'm not sure, and please throw it in the chat, you know, where are your system temps, where are they being designed, or where do you think your contractors, you know, what type of applications and water temps are they using? If you could throw it in the chat, I'd love to hear some feedback. You know, where I am in the entire United States, it seems 180 degrees is the temperature everywhere we go, right? Nobody has an answer why. Nobody knows why we use 180 degrees. So I'm going to share that information with you. If you don't know, I'm going to put it on that's going to be the next slide. So I'm going to wait here a second. But if you don't know, you know, or take a guess, you know, why do you think we use 180 degrees to heat a home? It's been one of those questions I've always asked, and usually the answer I always get is because that's the way I was taught. That's the way somebody showed me. I was told that's how we do things. You know, nobody has a specific reason as to why we do it. So I'm going to share with you, I did a presentation a couple years back, 2023, and I was doing an organization with a bunch of our oil dealers, you know, in the New York area. And, you know, I asked them the same question, and not one of them can answer. Some people kind of got close. They were guessing and throwing things out there. Most of them just trying to be funny with the answers. But when you think about it, and I did some research on it, and I found a gentleman that some of you may know. His name is Mr. Dan Holohan. And he happened to, when I say happened to, about 2 months prior to me doing my presentation in April 2023, he did a publication in February, basically called Why We Use 180 Degrees for Hot Water Systems. So it couldn't have been any more perfect timing for me to have to do this presentation and me doing the research. But basically, I'm not reading this entire thing. If you're interested in reading the article, because it is pretty cool, it's basically the history of the Carbon Club. It was done in Plumbing and Mechanical magazine. This is back in February down there. You can take a screenshot or look it up. You can find a whole article. Basically what happened was a bunch of boiler manufacturers got together. They formed a club called the Carbon Club. And what they did was they had a meeting, because at the time, you think about the systems, look at the date here, 1899. So in 1899, they had a meeting. They also had some issues with scarcity of cast iron. So all the cast iron boiler manufacturers got together. They did some stuff. If you read the article, it's crazy. A lot of illegal things they did at the time, as far as basically telling every manufacturer that they had to sell their boilers at the same prices. And if you deviated and sold a boiler less than that to a customer and they found out about it, they were going to give all your customers free boilers and put you out of business. So that was the kind of meeting this was. But the other part of that meeting was this, think about this, they had steam systems for the most part, 212 degrees of water temp. Then they went to gravity hot water. So we heat that water up. The controls were not great. So they were putting water out almost boiling. And as that water was boiling, obviously with gravity, hot going to cold, it created this flow. They did it on open systems, right? They were open to the atmosphere. So what happened then was pipes started to corrode inside. Once they started corroding, they started to hinder that flow that was going through, that gravity flow. So they started to develop a pump. In this case, it wasn't a circulator; it was a pump that it's called a booster pump, and B&G developed it. And what happened now is at 212 degrees, you go and put that pump on and push that water out. All that cold water that came back to the boiler would crack it, right? It would shock that boiler and crack it. So they had to develop a temperature that was less than boiling, all right? So they picked 180 degrees. That's exactly where they got 180. Now they did make it kind of a standard for some of the heating emitters that were out there based on heating surface. It had to basically output a certain amount of BTUs per area, based on that 180 degrees that they picked. But as far as the booster pump now and designing something called a 20-degree delta T, something we use for designing circulators now, hydronics. If you ever sat through a takeoff presentation, you've heard this before, talking about delta T and temperature drop, right? So they designed this pump around a 20-degree delta T because they were using a formula, and 20 made the math easy to do in their head. And this is where contractors kind of open up for me, because it makes them laugh a little bit. But the reality is we picked 180 degrees in a meeting in 1899, and it's 2025. We created a delta T because the math was easy to do in the head, right? In 1899, and here we are in 2025, and we're still designing systems around a 20-degree delta, and we're using 180 degrees of water. And that is it. That's the only reason. Right? There's no scientific reason why they use 180 other than that's what they picked, right? So when I talk about this, it gets a lot of funny laughs, and a lot of people, now they kind of are open to, wow, that's why? Oh, okay. So that's where I hit them with a lot of this manufacturer data. You look at all of these different types of systems that are out there today, from panel rads, baseboard convectors, air handlers, unit heaters. We've seen a lot of these out there in the field. I just pulled some stuff that I was familiar with. Radiant floor systems, they're talking about supply water temps anywhere from basically 70 degrees all the way up to 130, really up to about 150 is the max. Anything over here, we're worried about damaging floors. So that's radiant, and the guys are pretty comfortable doing that, but they're not used to putting 140 degrees through an air handler, right? We're getting BTUs, and that's what we need to teach them, is understanding how to deliver BTUs, not the water temp. If I look at a toe kick heater, we've seen these before. They're showing water temps down to 110 degrees. The only difference I got to make to this system, or the only change I have to make to this system, is I have to go get basically an optional low temperature aquastat to put on there so I can activate the fan in low water temp conditions. What else we got? Convectors. So we see these all over the country. Convectors mostly used for steam, but in the manufacturer's data, they have some correction charts here based on water. So that's this chart here, and we can pick various water temps all the way down. You can see what they considered standard was 215 degrees, but yet I can do water temps of 100 degrees here. So not that we can't do it, it's just about understanding how many BTUs we're going to get out, and is it going to match what I'm losing. So as long as we're matching it and we're offsetting those numbers, we can maintain a thermostat setting, right? I like using FinTube as an example because it is a very, very popular heating emitter of choice for many contractors, and we oversize the daylights out of it on almost every installation. So I like to use this example when I'm talking to contractors, because I show them two different charts here. You can see basically average water temp, and then some manufacturers even call out on the lower water temps ratings for condensing boilers. Right? So if I want that boiler to condense and be super efficient, I need to be in that water temp range, and that's average. So 130 average, that's 140 out, 120 back on a 20-degree delta. And then we got our GPM and all of that, and this is how many BTUs we put out per foot. So I use the example of 10 by 10 room just to keep it simple. And I ask them, I tell them not even to pay attention to the 3,500 BTUs, but I ask them, how many feet of baseboard would you physically put in this room if I told you there were 2 outside walls in this 10 by 10 room? And I just started recently getting a couple of guys, they're paying attention to what I'm asking, and they've said 20 feet. I've done 20 because you do both outside walls. And that's not the right answer, but that's what everybody does. And that's exactly what I was getting at, because that's what I use in my example. So if I took 540 BTUs per foot, saying that we're using 180 degrees supply water, 160 return, so average of 170, I get about 540 BTUs per square foot, per foot, sorry. If I did 20 times 540, I end up giving out 10,800 BTUs for 20 feet of baseboard in a 10 by 10 room that only needs 3,500 BTUs on a design day. And that's the important part. So on the coldest day of their year, on the design day, I need 3,500. Yet if I did 20 feet of baseboard, which is very common everywhere you go, you end up putting out about 10,800 into the space. And that's how oversized we really are from room to room. So if I were to now take that same 20 feet of baseboard, making no adjustments, not pulling any element out, not blocking any off, all I do is change the water temp to 130 degrees supply and 110 return. Well, that 100 or that 20 feet of baseboard is now going to give out 4,500 BTUs, which is still 1,000 BTUs over for my design day temp and the offset I need of 3,500. I'm putting 1,000 more BTUs in that space that I need. Now, you think about off of a design day, right? So an average day in the 20s, 30s, 40s, maybe depending on your region. Those average days, I don't need as many. So I don't need 3,500. I might need 3,000, 2,500. Yet without modulation, like an inverter boiler or our gas boiler, I'm always going to deliver 10,800, right? So getting them to understand how much we oversize and how we can kind of fix that with low water temp. Now, I'm a reality guy. I understand the applications. I came from the field, spent 19 years as a contractor, going to many insufficient applications, insufficient heating applications, where customers complain it just wasn't hot enough. And that's for some clients and some homeowners that may not be enough. The temperature just doesn't feel comfortable to them, even though the numbers are right and we're going to come close to satisfying that thermostat. Some customers just don't feel comfortable with cool water. They're so used to having the hot temperature. It is a change. Some people you can't satisfy, and we can't fix everybody, but by the numbers, we can do this all day long. And as long as the contractor understands that they need to basically, understand their expectations, the homeowner's expectations, at least we're a conversation, and that's all we're looking for at this point, is just to have a conversation. Let's look at the application. We may be able to flip something. We may be able to work with their current system if there's still some useful lifetime left on it, and we can run that hybrid system. Maybe my heat pump's going to do great for 80% of their winter, and then I got to switch over to the boiler, and that's fine. That's exactly what we're looking for, and that's going to be majority of the applications we see as this market grows. All right, so taking a look at some of the installation, we're going to touch on clearances and all of those guidelines. Obviously, snow is a big part of the north up there, so we have to be mindful of where we're mounting these machines. Obviously, they got to get up above the snow load, so we like to be at least 20 inches above. The snow is an inconvenience, I like to say, and I've dealt with heat pumps for a long time. If you have this thing blocked up with snow and we lose the airflow and this thing can't turn, you're going to get an error code. It's going to shut down. It's now an inconvenience because now somebody's got to go out there and shovel it. What I'm more concerned with is at the bottom of the machine here is there's a bunch of holes down there, and those are drain holes. So when we go into a defrost cycle, so if you're not familiar with defrost, I'll explain it real quick. But as we get down and weather conditions are within a certain, I guess, environment, whatever they are, but basically if we have enough moisture in the air and we can start to form ice on the back of this coil, right, we have to melt that ice at some point. We have to make sure that when that ice melts during that defrost, that it has a way to exit the machine, get out of there. If it doesn't and it pulls up underneath the machine or it gets stuck inside there because it's all clogged up underneath there, it's going to refreeze again. When it refreezes, if it refreezes around the coil and there's copper U-bends of the outdoor heat exchanger, there is that opportunity where it will, basically contract over it, and it's going to split the U-bend on there. So the copper can get crushed because of the ice. Now we're going to lose our refrigerant, and we're going to have bigger issues in the system. So it's very important to make sure these things are off the ground, not just for airflow, but for drainage. We want to make sure all that water can get out during those defrost cycles. Wall brackets, for some people, they seem to be popular. These are heavy machines. There are brackets out there that can handle them. We just have to make sure these contractors understand they have to be bolted properly. We already had one of our betas. The guy didn't put it all the way through the sill plate, so it actually pulled off the wall. Luckily, no damage, but that's the safety concern there as well. The other thing is noise. I've never been a huge fan of wall brackets, just because when you have a machine, any type of mechanical device on a metal bracket that's now bolted into a wood structure, you're going to hear some sort of a harmonic or vibration coming through there. If there's no vibration eliminators on here, you're going to have some kind of noise that may be a complaint. So I try to avoid it. And for whatever reason, it seems every time the contractor puts one of these on a wall, it ends up being like a bedroom wall or something like that, or very, thin construction. So, these things have to be thought about, obviously, beforehand. So we do have some clearances for being able to work on his machines, as well as for having proper airflow. 20 inches minimum when we have two units together. This way we can get inside. On the right-hand side here, there's a panel that comes off. It's also where the pipes are. The electrical comes in. So if there's anything that needs to be touched, electrical inputs are here as well. So we want to have some room for serviceability. If we are putting them against the wall, try to have about 26 inches minimum. Overhangs above them, we want to have about 40 inches of minimum space. And again, that's going to be for airflow mostly, right? We want to make sure we got good air coming through these things so they can breathe, and we can transfer that into the refrigerant and then the water. Any wall in front or below or behind it, we want 8 inches behind it, minimum 60 inches, about 5 feet in front of it. So again, mostly airflow, and a lot of times we can't help this. They get installed, everything's nice and clear. Homeowner wants to block it off a little bit. They put all kinds of vegetation or different construction in front of it just to kind of block it off so nobody sees it. So we just got to make sure they're communicating, contractors are communicating that to them as well, that we need those clearances. Some more things just to be mindful of are dryer vents, kitchen exhausts, any type of gas appliance termination. We want to make sure they're away from the coil. We don't need, in a dryer vent situation, we don't need that stuff getting in there, clogging up, and that's just going to increase the maintenance for these machines as well. Mounting the indoor units, fairly simple. The control box can be mounted directly to the wall, has some mounting holes in the back there. So we have the hardware that comes with it, so they can mount that. I forgot to throw the weights in here again, so I got to add that. But the hydro box, being the heaviest, is about 66 pounds with all the components in there. That will have a bracket just like how boilers do. They mount it, level it, all of that, and then just hang the hydro box on it. So that's fairly simple. Control box weighs probably more than half the weight of the hydro box, so 66. I want to say it's like 28 pounds to 24 pounds for the control box. Still want to make sure it's being secured properly, for sure. All right, wiring the system, indoor and outdoor. We'll start with the outdoor unit first on the left-hand side here. So we are 208, 230 single phase, minimum circuit ampacity 20.5. So we're looking at a max circuit of 30 amps. On a 5-ton, we're looking at a 60 amp breaker. Those are just minimum wire sizes. Indoor units, we can, on a control, I'm going to say it's going to be 115 volts most of the time. That's the way I'm educating guys. That's the way I wanted them to power this up. We can do dual voltage. The only, I don't know if there's a big benefit there, but if a contractor had a 208, 230 circulator option he was using, that would probably be the only reason why, because whatever we input to the machine, we send out. So if I brought 115 volts in, which is going to be the most common, all my circulator outputs, my auxiliary outputs, stuff like that are all going to be 115 volts going out. So if I put 115 in and I put a 208, 230 volt circulator in, there's going to be a problem, vice versa. I put 208, 230 in and I have a 115 volt circulator, I'm going to burn some circs out. So 115 is going to be my communication to most contractors, and I don't see any reason why to do anything other. Hydro box is 208, 230 volt only, so that's going to be input power. We have a 15 amp breaker for that. And then if we were going to use 3 kW element inside of it, that would be an external 208, 230, and that would be on a 20 amp breaker. So we are all about ratings. The 3 kW is rated at 230 volts. So if they were bringing in 208, then you would have slightly less performance. It's about 9,000, what do you call it? I'm sorry, it's about, forget what the number was. If it was 3 kW on 230, it's something like 2.7 something kW if you did 208. So there is a little bit of a deration there. The sensors that we do include are going to be the buffer tank and the domestic tank. So if we're using an indirect, we do provide those two sensors. We do have a room temperature sensor, electronic mixing sensor, and we do provide a communication cable, which is about 32 feet, can be extended up to 100. So all of these do have their identifications on the end, as you'll see in the next slide here. You can see the mixing valve coming out of the control box is labeled TV2. If I looked on the sensor here, it's also going to be labeled TV2, and the extension cable, that also has TV2 on it as well. So everything is pretty well labeled. Mistakes can still happen. I don't want to say that, you know, eliminates mistakes, but if it can happen, it's going to happen. We know that. So side by side, you kind of see the control box and hydro together, and we're going to look at the terminals themselves and their identifications. Quiet group today, not many questions. All right. So control box being 208, 230, or 115, I have it labeled that way. You can see the 115 is labeled on the actual diagram. So when a contractor looks at the IO manual, they're going to see that 115 volts. We have 4 separate circulator outputs here. So starting with left, we'll go from left to right here. We have what we call our P0 circulator. That's going to be our circulator that brings the water from the heat pump into the space, into the buffer tank. We have pump 1 and 2. Those are circulator outputs if we were controlling the pumps directly from our control. We'll talk a little bit about a little more towards the end of this slide, the other options we do have. Pump 3 is a dedicated recirc pump. So if we are using an indirect or some kind of water tank that has a domestic recirc pump on it, we can utilize this terminal to power that pump, and we can control it through our programs. We can give it, it's basically a 7-day programmable. You can set the times, the hours, you know, how long it comes on, how long it shuts off for. So all of that is built into the control, which is really cool. I have not seen that involved in anybody's controls, so that was pretty exciting to see it. I think domestic recirc is definitely something people are more, you know, paying attention to as far as water saving, stuff like that. So it does give us an advantage there. The next 3 next to it are going to be our auxiliary heating terminals. So we have what we call our auxiliary heat, which is basically works for both heating and hot water. And then we have our hot water tank backup heat and heating backup heat. So we have the ability to control the indirect backup or the buffer tank backup separately. And then we can have both of them energized off of the air handler. So you got some options here, you know, and depending on, you know, the contractor's applications and what he's doing, it gives us some room here to play around with not just maybe a hybrid or a fossil fuel boiler, but also if there were electric elements inside the tank, we can utilize the elements as well as the backup boiler, and we can switch out priority, which we'll talk about a little bit too. So if I want one to come on before the other, we have that. We do have a diverter valve terminal here, and then we have our communication. So that's going to be, you know, going from our indoor to our outdoor box. We got to make sure this is a it's a 3-wire with a ground. So, and it is a twisted shielded wire. So we do have to make sure that they're grounding this so that there is no communication interference and we don't get any errors. At the end of the strip here, I'm going to go to the end, and we have our cooling, heating, switchover inputs. So this is, I mentioned before, we have the ability to manually select what mode we are going to be in depending on the season, or we have the ability to do automatic switching. So we can do automatic switching, as you'll see in a few more minutes when we get into the control. We have a couple different modes we can do, but we have the ability to take an external signal, a dry contact, which is basically going to tell us I need cooling or I need heating. We have another one that I didn't call out at the end here, but this is a high temp. So, and when we mention high temp in the heat pump world, we're really talking, you know, they elevated 130 to 140 degrees. So if we did have a reason to have that, plus we had some radiant maybe running at 100 degrees, 110 degrees, we have the ability to have this kind of priority for high temp where you may be using electronic mixing at that point. So there's a lot of bells and whistles here and great features, but we can simplify this very nicely too. At exterior, so the outdoor unit, we do have our input power coming in here, 230, our communication, as you can see there. The systems that we do have that are coming in shortly will have additional terminal blocks there. They'll have the ability to control a circulator from the outdoor unit, as well as having a diverter valve or, you know, mix valve there. So you'll be able to wire everything directly to that. That's going to come in down the road when we start talking about cascades and stuff like that. So stay tuned for that. All right, piping. All connections, whether it be the outdoor units or the indoor hydro box, are all 1.25" MPT tappings. So the contractor can put his choice of fitting on there, whether he's doing PEX, copper, you know, whatever he chooses. If he has a flex line or vibration line coming off of this, you know, he gets to pick the material. So we just want to give them something solid to come off with. The actual labels here, really nice. So identifying what's going to be our input in leaving water temp, so leaving and entering. So hopefully they don't screw that up and pipe it wrong, but it could happen. Obviously it can happen, but they do a good job of labeling these machines, so it prevents that. Buffer tank, those are some great conversations. When we talk about buffer tank, there's a lot of different ways to pipe them. Mostly we're going to see the 4-pipe as you see here on the left, where we're going to have our supply return from our heat pump. That's one system. And then we're going to have our supply return from the heating system itself inside the home, whether it be radiant, panel rads, you know, fin tube, whatever it may be, totally separate from the heat pump, right? So the heat pump's only mission is to make sure this tank is staying at the temperature that we designed or we set it for. And that's it. And then both of these flows from the heat pump versus the system could be 4 GPM to 9 GPM, could be 20 GPM to 9 GPM. It doesn't matter. They're going to work independently. We have some good hydraulic separation. One of the, you know, great features of a buffer tank. It's also some extra protection there, depending on the volume of this tank. You know, helps with defrost cycles. One of my favorite configurations, right? We call this a for direct to load configuration. The only main difference here is that instead of bringing my system supply off at a 4th port here, I'm going to create what we call a short large header off the front tapping of this tank, and I'm going to have the heat pump supply come in, and I'm going to go out to my system supply. And what that's going to do is that's going to guarantee I'm going to have the hottest temperatures or the coolest temperatures, depending on the mode, coming from my heat pump and going directly out to my emitter. So I don't, what happens with a 3-pipe is I don't necessarily blend as much here. So whereas a 4-pipe, I bring in some hot temp here, I bring in cool return water here. It's going to blend this system down, right? So now it may not be the same water temps that I'm bringing in. It might take for that system to recover and get those proper temperatures. So if my system or my application is you know, sensitive to the water temps I'm designing around, I may want to look at a 3-pipe compared to a 4-pipe, you know. So, and again, as these applications come around and we have these conversations with contractors and then look at their system and then look at what they're designing, we'll be able to make those recommendations and help them with that. Basically, what I just explained is here in this illustration is just having 2 different systems, having, you know, 2 different flows and having total hydraulic separation. 3-pipe, same deal, right? Hydraulic separation still happens because of that short header. If we were using a hydro box, all right, the hydro box is going to look something like this. So we have the heat pump supply coming out, and so that's outgoing water, comes in through the box. We have a circulator built in there. The diverter valve is then going to, based on the mode we're in, whether it be domestic or in heating, it's going to divert that water either to the buffer tank or the domestic hot water tank. From there, we go into our heating system, our returns from the both the indirect and this through the buffer tank, and they're going to go to the heat pump themselves. So that's what the hydro box looks like. I think, you know, we've talked, and Dan and I have talked about this, contractors and I have talked about the hydro box. You know, it's kind of mixed still. We're anticipating more on the control box than on the hydro box. Again, contractor, does he want something that's pre-packaged? Does he want to build it himself? It's really going to come down to a couple of different things. Maybe cost, I don't know, but you know, these are all the things when we're looking at a system design. You know, typically if I'm not using an indirect tank, you know, or even if I am, I may go control box. I can add a diverter valve. I can put my own circulator in place. They have any internal is great if I have a short system, meaning that I can have the outdoor unit close to home. Maybe my mechanical space is right there. There are some little pumps, so we got to think about that when we're designing the system, is how far away, how small, large. So again, when we size these things, we would love to be part of those conversations to help you. And that's correct, Stacy. Yeah, as of now, as Stacy mentioned, I don't know if anybody can see that, but as of now, NTI does not have a buffer tank. That's something in the works. It's kind of behind the scenes. You know, Dan's working on that, and we're waiting. So yeah, buffer tanks and indirects, hopefully in the near future. So, but yes, they can use anybody's buffer tank at that point. They're not specific to NTI. And what I find just dealing with contractors, they all have their favorite brand. They all have different, you know, tanks that they do like. So if they do have one that's specific and that one Emco's, you know, selling, then we'd be happy to fit that into a design for them for sure. Excuse me. So freeze protection is a big conversation. Anytime we got water pipes running outdoors and we lose electricity or something, we want to make sure we have some protection there. So depending on a region, we push contractors to just reach out to whoever's glycol. Not sure what Emco has available as far as a glycol, but there are recommendations typically right on the bucket that's going to give them all this data that they need to make sure the system's properly protected. We do have some internal protection for when there is electricity there. If it's normal operation, the system has the ability to watch outdoor temperature and the water temperatures. And if they start to get too cold, it'll either turn the circulator on or it'll turn the circulator plus the compressor on, just to make sure we got some flow, we got some hot heat going through the system. Not so much, we're not going to overheat it, but it's just enough to prevent any type of freeze. So we want to make sure we got good insulation, good glycol concentration, and the system will be fine. Insulation, as I just mentioned, is a huge topic as well, especially if we're dealing with chilled water applications. First time somebody deals with it, I'm going to tell you right now, they do not insulate it properly. If they've done applications with chilled water, they understand that every single metallic part of the system is going to sweat. If the dew point is right in that mechanical room, every ball valve, circulator, air ventilator, air separator, sorry, magnetic filtrate, anything that's going to have that water going through it from 45 to 60 degrees, if that dew point is right, it's going to sweat. So having the proper insulation, and this is that I saw Nelson do. It's a guy, I believe he's in the States here. This was a job he actually went back to as a contractor to re-insulate somebody else's project because they didn't do it properly. So it's something we just have to be mindful of, not just because of the sweating, but we want to make sure that all those BTUs, every single one of them that we're creating, is getting in and we're transferring it into the space as best as possible. One of the things we do have available, this is on our website now, we do have some piping diagrams there that you can find. What we also have that's in the installation manuals as well is these, you know, basically good starting points for a design. So we're giving you the basic piping, we're giving you the bare minimum as far as what sensors and wiring we need. So you can, you can see here that we have 4-pipe system. We need a buffer tank sensor going back to our control box. We have a circulator output going back to the control box, and we have a communication cable going from indoor to outdoors, and they're all called out here. So this is just a little sample of a basic central heating cooling with a buffer tank. From there, we give them where are we going to land these terminals, so they can see it on the piping diagram. Now they can kind of see it from the inputs outputs of the control box, as well as the outdoor unit terminals. And then finally, we give them some basically minimum setting parameters that may need to be changed. And you'll see here that they have a default, the range that they can be adjusted, as well as the recommended setting. Some of them, as you can see here, are labeled up to user. So these will be, generated based on the application. And again, that's something we'll be able to help them with for sure. And there's about 2 or 3 pages of them for the heating cooling with a buffer tank. And then same thing, I didn't put all the pages here just for time's sake, but for central heating cooling now with the addition of an indirect. Now we add the tank, now we need a diverter valve. So again, you're gonna see the minimum that we need as far as sensors. We do have other features that they may wanna take advantage of, and that may be in addition to this, but this is kind of that minimum of what they need to get a system operating properly. And then we have the same thing, heating, cooling with a DHW indirect, as well as a hybrid application now integrating a boiler, right? So these are meant really just to kind of get somebody not familiar with piping a system, give them basically a baseline here where they can start their design from, and then from going on, basically building this project, we can help them with any type of manipulation of this schematic. So we can go through the control here. We look like we're doing pretty good on time. So as far as the control itself, you saw the home screen before to navigate, you get this great information. Now we're going to go through how to enter the control, how to get into it as an installer, and then some of the features that are there. All right, so first things first, we get into the bottom of the screen there, the bottom right of the main screen. It's going to have a little setting button. It's going to bring up this screen here. If they scroll down, that's the extension of it, where there's a lot of different options here. We have ability to get into our heating and cooling circuits, domestic hot water under sanitary hot water, working mode. This is where we're going to really tell the machine what we need to do, system settings, timer, a bunch of other stuff, and we're going to go through all probably the most important ones here today. So in order for me to do anything as far as adjusting parameters, I have to first get in as an installer. So if I hit the system settings button, what I'm going to find is at the top of the page, it says permission level switch. So I'm going to go from an end user to an installer. So I click on that. It's going to bring up my password screen. I'm going to bring in basically count down from 8 to 1. So that's my password. Hit that little blue button or blue arrow on the right there. And then I can confirm at the top of the screen that it has switched and we are now an installer. So that's going to expand on a lot of those menus. You can still click on them. It's just maybe going to give you some limited views on what's there as an end user. So an end user can't go in and start changing things up. One of the great features that I think so far contractors have liked, it's something I have not seen, so I try to bring it out as much as possible, is once a contractor gets in front of this machine, whether it's us helping them or they're comfortable doing it on their own, and they program everything they need to do, they can come up to this page again and go hit save settings. And what that'll do is, God forbid the homeowner found out the password. Everybody can find something on Google these days. But if they had the ability to get in there and find it, and they went in there and fumbled around and touched it, or another contractor even was there and fumbling with it, the contractor can go back and reset everything, as you can see down here below, to his settings or to factory. So if everything was still there and he had it saved, all he's got to do is hit that and it's going to go all back to where he had it. So that was a pretty cool feature. So next we're going to look at our working mode. So when I get into working mode, we have operating modes, we have our basic operation, what else did I have here, and auto functions. So basically here is I'm going to toggle everything I want this machine to do. If there's no indirect involved in this, so obviously I'm going to leave this off. If I'm doing heating and cooling, I'm toggling it on. So when you see the blue, that means it's on. Basic operation, default is off here. And basically what that means is we're going to control our system by water temperature. There is the ability to control by room temperature control. Basically then you need, as you can see at the bottom here, a room sensor that is needed. That's not a very popular way of controlling it. Usually we'll want to monitor our water temps, but it is, if somebody is asking or looking to control it that way, we can do it. Auto function for heating and cooling, this will be popular. So here we have a couple different options, and we do have, if we're using ambient temperature, we can pick the temperature to start heating as well as to start cooling. So if I click on the, and I'll go back one more, if I click on the auto function for heating cooling, it's going to give me three options. I can do ambient temperature, where it's just going to watch outside temp. If it's just watching outside temp, as you can see down below, our start temp for heating and cooling, basically anytime it's, and this is not something that, this is not a realistic setting here, but I could say, all right, at 70 degrees, anything above 70, I want this to be in cooling mode, ready to go. I would put 70. Anytime it goes above 70, it's going to be ready to go and standby for cooling. If I put it on, or less than 59, it's going to be ready to heat. So the machine will switch, run in those modes when it's less and above those temperatures. An external signal with ambient are probably going to be the most common that we do see. I feel the external signal is probably going to be the most popular. What that basically means that with any dry contact I bring in to cooling supply or heating, or sorry, cooling switchover or heating switchover, that's what's going to drive the machine to turn on and run. So if I had a third-party relay, Takeo, whoever you sell, Residio, there's a bunch of them out there. Whoever's relay you're using, if I run their end switches back to this control and right to these terminations here, anytime one of those zones calls, that relay is going to control whether it be a zone valve and circulator or just a circulator. It'll turn them on and it'll function right from there. But it's going to allow us to say, all right, I'm in heating mode, one zone's calling or 5, doesn't matter how many they have. It's going to now tell my machine to go on, and I'm going to go target my buffer tank temp, which we'll take a look at. But all of that is done through a dry contact, or what we call an external signal. And those are your temperatures right there and the ranges. From there, we can get into the heating cooling circuits. So we have circuit 1 and circuit 2. A lot of stuff going on here. It may look confusing, but it's very easy to kind of manipulate and change. Not a lot has to be changed. Realistically, it's going to be our fixed water temps. So here I have the ability to change my temp. So if this is the case and I need this thing to maintain 120 degrees in my buffer tank or 110 degrees in my buffer tank for heating, I'm going to set that temperature here. And anytime I get an external signal saying I need heating, it's going to look at the set point, the actual tank tank temperature, and it's going to use these kind of deltas here to decide whether that machine needs to fire up and maintain that temperature, or are we good? We can stay until we draw out some heat, right? The same thing for cooling down here. So those are going to be very popular. We also have the ability to set some curves here. So underneath, you can see adjustable heating curves, which is outdoor reset. We have here room temperature reset, which is down below it. So again, if I'm doing room temperature reset, I have to add a room sensor, which we provide, but you would have to add it to the system. Outdoor reset's going to be very popular. We actually have a call this afternoon that's going to be, a big topic is, can I run this like my boiler with an outdoor reset? And yes, we can. So we can have a heating curve as well as a cooling curve. So we can have outdoor reset for both modes. And here we can change our parallel or our temperature here. So what that looks like is right here, right? Here's minus 59 degrees Fahrenheit, and I can select and build a reset curve for that application right from this menu here. So we're picking our ambient temp, we're picking our set point we want to maintain, and the machine will do the rest, all right? From there, we got sanitary or domestic hot water. So again, if I have an indirect being used, I can set my tank temp using our sensor. We'll monitor that temperature. We have our restart delta T. So when that tank drops down 9 degrees, we're going to fire and we're going to get that thing rocking. We can do heating and DHW shifting priority. Again, we can pick an outdoor temperature when to have priority. So if I'm warmer outside and I don't need the priority of heating, cooling, right, I can turn, or I can set a temperature at which I want that priority. So those are cool little modes there. Then we have some minimum working times, high temperature limits, stuff like that. You saw this before going through the ambient temperature screen, and you click on the ambient temperature on the home screen, it'll get us into these parameters overview. If I go into parameters overview here in the settings menu and I drop down in the refrigeration view to setting, this will give me the opportunity to set the machine's exact configuration. Again, this will be more important as we get into cascades further on, where if I have multiple outdoor units, the working mode is going to tell me what the entire system does. The device configuration down here is going to tell me which individual heat pump does. So if I have certain heat pumps that I'm going to dedicate to the heating, and then I need all of them to do DHW, I have the ability to do that. The same thing with cooling as well. So that'll be more in the future. This will be a big player for us when it comes down to hybrid systems, right? Electrical and backup heater settings. So here we can turn on, do I want it for heating? Do I want it for hot water? Do I want to deactivate the auxiliary heating? Priority switching, as you can see down here, if I do heating backup heater and I activate that, well, this is going to be basically a start time. This down here is going to be my priority. This is going to tell me which one. Do I want to activate my auxiliary heating before I do my heating backup, or vice versa? So you have all of that right here, right from that screen. So we'll see this a lot. We also have, as you see down here, is ambient temperature. So basically any time that I'm less than, 32 is kind of the limit. This is a limit for that, I'm sorry. And then this is going to be my, okay, at less than 59 degrees outside, I want to activate it. That's pretty high. I'll probably drop that a lot, but you can select what temperature you want to make that active. And the machine's going to look at its algorithm, see where its set points, and it's going to control all of that internally of the machine. Another popular setting that we may need to get into is the water pump settings. If we're using a hydro box, a lot of this is programmed as far as the P0 pump. But if we're using a control box where we don't have a circulator, one's going to be supplied by you guys and a contractor, then we have to go in and tell it what we're working with. We have to tell it that we're using an AC pump and not a PWM like our hydro box. We then don't have the ability to change our working mode, whether it be interval, on, off, continuous, or off with the compressor. So we have the ability to control that. Pump off intervals, again, if I'm using interval mode, here I can select whether or not I'm using a buffer tank. I mentioned before, if I'm not using a buffer tank because my system volume exceeds what my minimum is for that application, well, then I'm going to turn that off, but I'm going to take my buffer tank sensor and I'm going to strap that to the return side coming out of my buffer tank going back to the outdoor unit, and we'll monitor our temperatures from there. If we are using the circuit circulators, P1 and P2, we can designate what they control. So if there is or when they come on, I should say, if there's a high temp on a dry contact, a cooling or a heating, it will automatically activate those circulators as well. And as I mentioned before, with the recirc being on P3, here is your schedule. So we can activate it by toggling this on, and then we can set a schedule up to 6 different times a day, 7 days a week. And we can also change the runtime as well. So save some controllers, maybe saves a couple dollars on site, might be a good option. Some other settings we do have if we're not using the hydro box itself and we are using somebody else's diverter valve. I'm not sure which valves you may be familiar with, but if you were going to go use another valve, then we need to go in there and program the switching time of that valve. So every manufacturer has a different switching time. We have pre-programmed 6 minutes for the one that's in our machine. So basically with that, in between a domestic and a heating call, how long does it take to switch that over? And we're using 6 minutes. We set that. This way we're not turning a circulator on before that valve is totally switched over. So we do have, again, for domestic hot water, if we are using it, we have an anti-Legionella function in the machine where, we have the ability to set a program. Typically when people are sleeping, we have the ability to turn this thing on and really raise that tank temperature above 140. This way we can kill any type of pathogen that may be in that water or growing inside that tank. So in certain regions, I've been asking this question a little bit. I'm not sure everybody's code at this point, but a lot of different areas we have to maintain tank temps over 140 degrees and mix it down with an external valve just for this one reason. So if they don't have to do that, which seems to be common in a lot of other areas too, we have the ability to turn this mode on. So periodically we will that we're not having any of that Legionella going on. The fault history and the fault information is, this screen is very, very informative, especially for somebody that has never dealt with air to water before. I think a lot of us have agreed that have been working with the machine that this is probably our favorite part, where we give you indoor and outdoor errors. If there were one, we can go in there and see what they are. But if we were to click on an error, and I created this one in our lab up in down in New Bedford for you guys, I created this error by basically not having a indirect sensor there, but telling the machine that it was going to do domestic hot water, and it gave me a temp sensor failure. It'll give me the time date. It'll tell you how long the duration that the error was present, because some errors may pop up and may fix themselves, and then you don't know they're there until you go back into the history and you take a look at it. But it's going to give me some possible cause measures to follow. So tell me at least to take a look at some things. It's also going to give me some treatment measures. So it's going to tell me what could cause it plus what could fix it. So I think this will be great for anybody coming into air to water for the first time and not familiar with the machine. You know, it gives them some really good basics, you know, to start troubleshooting. We always have the ability to upgrade the software as needed. That's something that we determine if we do need to send out an upgrade. You know, if it's application specific or, you know, specific to the machine, or general upgrade on the software, we can do that by putting some files on a USB thumb drive, as you see here. Plugging that in, we have an instruction sheet if that were needed to be happening, and it's as easy as sending them over an email, which has been great. So that is available. So as we're kind of winding down here, I'm not seeing any other questions popping in. I saw Stacy's comment, which I appreciate. So talking about strategy and market and who we're really looking at, right? You know, the contractors that I've been focused on, really trying to have conversations with, are really the energy efficiency guys, obviously, whether it be heating or cooling. Plumbers in the area that don't typically do air conditioning are great targets, because it really gets them into this market for, you know, chilled water cooling with an air handler. They may not do the duct side, but if they get the equipment there, if they can work with somebody on the duct side, you know, it really gives them something new to work with. I've had in the past, like I mentioned early on, I came from the refrigerant side of the business, you know, working with mini split manufacturers. I worked with plumbers on many other hydronic products. And I've done presentations in front of them where they've told me, you know, I got to go get into the air conditioning. I'm going to go hire guys. I'm going to get the tools. I'm going to get licensed. And there's a huge, huge dollar to that. And really, to be competitive and for them to make money in this, they're never, ever going to be able to work or beat I guess you can say, or compete against this, number one, for a long time. But plumbers typically have a heck of a lot higher overhead. So for him to be competitive and him to make any money in this, these guys already know pumping and piping. So everything they need to physically do the system, they already know how to do it. They just don't understand it yet. So us educating them, whether it's, you know, coming up north and doing some training up there with contractors, or, you know, we do have the ability. I know it's a little bit of a hike, and you'll see it on the next couple screens, but we have the ability on the classroom side. We have our facility in New Bedford. That in New Bedford, we have the ability, 2-day training. I put my first class together. I think we did it 2 weeks ago. Had a group of guys up there. We try to keep them as small classes, 10 to 12 guys. This way we can manage it a lot easier, and they get all the attention they need. But they're going to have the ability to learn a lot of what you just saw today. They're going to learn a little bit more in depth on how to properly size circulators and pumps and all of that stuff. But we get more in depth on the second day, where they're physically building a system. So they have, I got a company to make me up some replaceable hoses. They're basically big 1.25-inch hoses with these cam lock fittings, so we can keep recreating this over and over, class after class. But they're physically going to pipe, wire, go through the controls, set up the controls for an air handler application. We have the air handler there, but they're going to pipe it all in, and they really get to, you know, see what it's like putting a system together and how it runs. And I got to say, for the first group we had up there, it was pretty impressive. I didn't touch a thing, that was probably my favorite part, is I didn't have to touch it all and build it and all of that. But watching them physically do it and give them direction and talk about every step of the way, the comfort level leaving that class was so much higher, obviously, than them when they came in the door. And these were all guys that have never installed a system before. So they were pretty confident they can go out just with that basic training there, that base, and they can go out and install a system if they had to. Obviously, it doesn't end there. You know, me being out in the field and work with guys is something I'm really looking forward to. But as on the contractor front, those are really the guys we're looking for. What's interesting is in the last 5 years before I came on board here, I want to say primarily 90% of the conversations I had about air to water systems came from homeowners. And homeowners are going into a lot more of these home shows. They're getting involved more. They're getting educated from, you know, whether it be on TV or wherever they're getting their knowledge. But I'm getting primarily all my phone calls coming out of the rep world were from homeowner-driven conversations, looking for a contractor that's capable of putting this system in. So homeowners, you know, if they, you know, I guess however they get marketed, they're going to learn about the system and they're going to be looking for guys that are capable of doing it, you know. And I don't need dozens and dozens of guys in your area. I need, you know, each branch has 1 or 2 good guys that can do this, and that would be a home run. Builders and developers, right? Efficiency focused, lead passive house, net zero homes. We've already had a couple email communications. I know Dan and I have had a couple come through where guys are looking at net zero homes, net zero projects, you know, and those are going to be great for this. Areas with electrification, I think it's everywhere at this point. Electrification is a conversation. Schools, municipal, bigger projects like this are great too, because, you know, we will have those capabilities of cascading. So having multiples there, they'll be great. But these are all just a little taste of who we're really looking to target with this product. I had this. These are, I'll go over this kind of quick. You guys can see this if you want to take a picture of this or a shot if you're on a computer. Stacy, I see yours. I'm just gonna, perfect, thanks, Dan. So Stacy was asking, just so everybody else can see, I don't know if that went back to everybody, Dan, or if that was just back to Stacy, but the R32.
It should have went to all, yeah.
Okay, cool. Perfect. All right, good. So you see the responses there. Yeah, so on the frequently asked questions, I put this together because these are the questions that I've been hit with in the past, and I think these are the most common questions that seem to keep popping up. And it's, you know, really an understanding that the machine can do both heating and cooling, you know, and possibly DHW. So I throw that in there. You know, how does it perform in cold climates? I think that's always a concern, you know, and that's where being able to, as we kind of get this thing launched and get closer to, you know, the end of the year here, we'll have the ability to cascade these machines, you know, where we may need to add another, or we may need to go the hybrid route with a boiler, and that's kind of the approach we have. I'd love having some kind of a backup, so having a gas boiler as well as the indirect, where we're not doing 100% of the load on either machine, is going to save the most energy for that home. And we also have, God forbid something happened to one, we always have a backup there. So we do perform well in cold climates. Understanding how to design a system properly is going to be the most important part there. It is more efficient. We talked about COP. I get that once in a while. Can it be used with radiation? And again, this goes back to, you know, doing a proper heat loss. We need to understand that envelope of that building or home or whatever it is we're trying to heat before we really start picking product, and how we can reduce that load. So that's been a big too. Eligible for rebates, yep, talk about that. Can it be integrated? Yes. Domestic may need to have that backup there. So if we are doing a heat pump and it's not maintaining in cold temps, there to resort on those temperature is great. When we talk about the temperature, everybody wants to know what the max temperature is. And again, I think this kind of goes back to those same questions of, you know, or not questions, or the comfort of heating a home at 180. Everybody wants to know the maximum. Usually if they're asking that, typically the conversation is because they're thinking domestic. But if it is on the heating side, you know, I'm not worried about the max. It's the ideal temperature where I want to design is anywhere from, basically 95 to 110 degrees. 120 is my design area. Can we go hotter? 131 degrees? Absolutely. 140 if we needed to. Yes. Backup heat needed. Again, heat loss, retrofit. Again, same stuff I keep saying is it really comes down to design. So if we apply it properly or design it properly to these applications, we're going to be a lot better off. We did put this together. We got to add maybe some stuff here too. Maybe I got to update some of the stuff, but this was just more of a competitive cross-reference sheet here. If you guys, seen some of the other machines that are out there, this file is actually, this is just a screenshot of a partial part of it. It is probably 15 systems on here, if not more. But just looking at some of the other additions, right? There's a lot of other people that are out there. We're all using primarily R32. These guys have all updated their equipment to R32. So we're all, as far as water temps go, we're pretty much a level playing field. We may say we can do a little bit more, short period of time. A lot of these guys are putting out the same piece of equipment. They're just branded under different names. So a lot of them are on that same level playing field there. But to do a lot of what we do already in our control box, most have to go with additional controls. As you can see here, there's a lot of additional, where everything is included in the control box here with our system. So with that, I mentioned the training. If you were able, or you had a group that you were going to come down, we've had some interest from up in Canada for this class. I've got a couple people, got possibly one coming down. So in the near future, but we have one coming up next week, 29th and 30th, and then we have two more dates out there, the 18th and 19th. This will be that 2-day training. So if there is somebody interested in coming down, please reach out and we'll be happy. The dates are on the website. So if you had somebody that was interested and you wanted to direct them to ntiboilers.com, they can go to our resources and training, and in a drop down for the dates, they will find all of them there. So we've done a couple classes already. So contractors we've met with, we've done some webinars with them. I'm kind of getting around a little bit here and there now, doing these trainings on the road as well as in our New Bedford facility. So we do have the ability. We also have one of the units up in St. John. So that's something that we could do in the future as well. We have one, not so much as a hands-on being able to build a system, but we do have one operating there. So that is always accessible.
Thanks for watching the video today. If you'd like to check out more videos, see the link below. Don't forget to like, share, and subscribe to our channel for all the future updates. And also check us out on Facebook, LinkedIn, and Instagram.